Hi, and welcome to the last lecture of the course, where we're going to talk about Fourier analysis. Okay, so what is Fourier analysis? So, sort in broad strokes, Fourier analysis is about representing functions as sums of nicer functions. Now, this is a pretty broad definition of Fourier analysis. We'll look at some specifics in a second. But if you can represent a function as a sum of nicer functions, then you can also approximate it, right? And I guess I'm being vague here. By nicer, these will be basically trig functions. Because you kind of already have some idea about how to approximate a function as a sum of nicer functions, and that is the Taylor series, right? So when you have a function with, I guess, you require it to be infinitely differentiable, you can find its Taylor series, and that's a way to represent the function as an infinite sum of powers of x, right? But once you've represented it as a Taylor series, you can also approximate it by cutting off that representation at a certain point and forming the Taylor polynomial. Okay, Fourier analysis is the same sort of philosophy. We're just not going to represent it with polynomials. We're going to represent them as sums of trig functions. Trig functions are periodic, and so if you want to study certain periodic things like waves or whatever, right? So like in signal processing, it turns out that Fourier analysis is a very, very useful, very, very nice thing. That said, what does this have to do with linear algebra, right? So you learn Fourier analysis in other classes, in applied classes, maybe in engineering classes, but how can that be linear algebra when trig functions are certainly not going to be linear in any way, right? So how is this linear algebra? It turns out that it is linear algebra. And if you can leave the lecture today with an idea of how knowing linear algebra helps you do Fourier analysis, then I think that'll be a successful lecture. Okay, so what we're going to do is we're going to let V be the space of all continuous functions from, okay, let's say 0 to pi to c. Okay, now there's a lot of different ways to introduce Fourier analysis. So you could talk about periodic functions with period 2 pi, which is actually what's done in the notes, but I think it's actually better to just focus on functions defined on this interval. This interval can, of course, be any interval. It's sometimes on negative pi to pi. You can also scale everything, so it's 0 to 1. That really doesn't matter. Okay, but this space is, of course, huge, right? If you look at all possible continuous functions on the interval to c, that's going to be, I mean, you could draw a bunch of continuous functions from this interval to r by just drawing any curve that you want, right? So this is a huge space. There's tons of functions. Uncountably many functions that are continuous from 0 to pi to c. But this space does have a nice structure because if f and g are continuous functions, right? So these are both functions from this interval to c, then we know that if you add them, there's a notion of adding them. What does this thing do to a number x? It spits out the number f of x plus g of x, which is a number in c. So f plus g is also in V. So you can add two continuous functions, and you get a continuous function. That's all I'm saying, right? And if alpha is a complex number, then I can define a function alpha f to be, you just multiply the output of x, f under x, by alpha, right? Again, the codomain here is c, so these things end up being complex numbers for every x, right? So the point is that V is a vector space over C. But it's a humongous vector space. It's very infinite dimensional, you could say. Right, so this is infinite dimensional. There are just tons and tons and tons and tons of functions. Okay, but essentially what the power of Fourier analysis does is it identifies a really nice basis for this vector space. Right, so in Fourier analysis, we identify a very nice basis of V. Very nice in that we understand the properties of the functions very well, and also very nice in the sense that, okay, well, first of all, since it's a basis, it means that every function will be a linear combination of those basis elements. Now, of course, it's an infinite basis, so you could have an infinite linear combination. But it's an even nicer basis in that if you take most of the functions that we are interested in, we'll identify the first few terms of the basis as sort of being the most important ones. And so you could approximate a function by taking some of the terms in your Fourier series. The Fourier series will just be the linear combination in terms of the basis elements. And so we will not only have a way to express every function as a linear combination of these basis elements, we'll also have a way of approximating the function by taking just the first few terms in that linear combination. Right? So this is going to be nice in two ways. So each basis element has nice properties. It's a nice function we can understand. And we can approximate functions nice functions using just the first few terms. Right, the point is that even though there's tons and tons and tons of continuous functions, if you're like getting a wave from some actual data, the waves that you're looking at aren't just random continuous functions in this space. They're really, really nice continuous functions. And so they should all sort of live close to some relatively low dimensional subspace of the space of all functions. Okay, so I guess I should just tell you what our basis is. So here's the definition, or we're going to call this function, oh, we're not going to call it anything. We're going to look at the function e to the I n pi x. Sorry, e to the I n x, where n is an integer. Okay, and of course, e to the I n x you can also think of as cosine nx plus I sine nx. Okay, now there's a bunch of functions here, right? One for every integer. I'm going to have a ton of functions here. But we can understand these functions somewhat because they have a nice representation. I've just written down a very nice representation of the function, right? So what are these functions like? Okay, well, let's consider for the zeroth one, right? E to the I 0 x. Remember, x here is a variable. This is a function of x. This is, of course, just, it spits out 1 all the time. So this is the constant function 1. Okay, that one's kind of boring. For every x you plug in, you just get 1. What about the first one, e to the I x? What does this do? Well, e to the I anything is going to be a vector on the unit circle in the complex plane, right? Here's the complex plane. Here's the real part of z. Here's the imaginary part of z. Here's the unit circle. Right, so this point here is 1, which is e to the I0. This point here is I, but that's e to the I pi over 2. Right, this one is e to the I pi. This one is e to the I 3 pi over 2. But this is also e to the I 2 pi. So what does this function do? E to the ix, as you vary x, wraps around the unit circle. Right, so when x equals 0, it spits out this point. As you increase x, it goes in this counterclockwise direction. As you decrease x, it goes in the clockwise direction. So what this does is this function, as x varies, e to the ix wraps around the unit circle in C. Right, at the first one is every 2 pi, you wrap around the circle once. Now, if I consider e to the I2x, let me leave it on the slide so that we can actually see compared to everything else. What does this one do? Well, this one does the same thing. As you vary x, it's still only ever spitting out vectors that are on this unit circle. The only difference is that as you go from x going from 0 to pi, you wrap around once. So this function wraps around the unit circle, but at twice the speed in terms of x, right? If you vary x half the amount, it wraps around the same distance as the first function, right? So this wraps around the unit circle at twice the speed. So all of these functions, e to the I and x, do this thing just at various speeds. And of course, if you put in a negative, then as x increases, you're going clockwise around the circle rather than counterclockwise around the circle. Okay, so these are very, very simple functions, right? Each of these, maybe I should have specified that these are functions. Okay. We only took it from 0 to 2 pi, I guess, in my introduction. So I guess I should say the first one wraps around the unit circle once. The second one wraps around the unit circle twice. The nth one wraps around the unit circle n times. And if it's negative, it wraps in the opposite direction. Okay, so these are very, very, very nice, easy to understand functions. And it turns out, we're not going to prove this, that these functions form a basis of V. So fact, if you take this set of functions, e to the I n x, where n is an integer, this is a basis of V. It's, of course, a very infinite basis. It's even sort of doubly infinite, right? You can go in either direction, but they form a basis of V, which means they're linearly independent, and every function can be written as a potentially infinite linear combination of these basis elements. Right, so every continuous function f from this interval to C is a linear combination of the e to the I n x. Okay, now V is not just a vector space, a huge vector space. V actually is an inner product space, which is covered on, we covered a little bit, well, we at least introduced an inner product earlier, this in the last few lectures. It's also covered on some homework. So V is not just a vector space. It is an inner product space. In other words, there's some notion of like a dot product between vectors in this space. But vectors in this space are functions, right? So what is the inner product? The inner product for two functions f and g living in V is defined as, so this is the notation we use for inner product in general. So this is how you take the inner product of two functions. What you do is you integrate from 0 to 2 pi f of x, g of x bar dx. Okay, I'm realizing that since I chose 0 to 2 pi, this disagrees a little bit with the notes. So you can change every 0 to 2 pi to be negative pi to pi if you want. It doesn't actually change anything. Okay, but this thing spits out a number in C, right? You're doing the definite integral over this interval in R of a bunch of complex numbers, so you're going to get a value in C. So for every two functions, you'll get some different value of C. But because we have an inner product, we therefore have notions of lengths and angles inside of the space, which is a crazy thing to think about, right? These vectors are functions. They're continuous functions from an interval to C, but there's some notion of geometry between the different functions, right? So in particular, I can now define the norm, well, the squared norm of a function to be this value, which is the same thing as integrating the modulus of f of x squared dx. And so this is actually a real number, right? It's even a real number that's greater than or equal to 0, I should say. So what is the length, what is the norm of these e to the I n x's squared? Let's say, well, you just integrate from 0 to 2 pi e to the I n x times the conjugate, but the conjugate is just the reflection across the real axis, right? And so what that will do is it will just negate this e to the negative I n x dx. And so you're just integrating 0 to 2 pi dx, and you get 2 pi. That means that each of these nice basis vectors has modulus the square root of 2 pi with respect to this norm. Okay, so I've got, sorry, the zoom thing, but so I've got a bunch of nice basis vectors, and I even know their norm. Okay, I can also talk about what's the inner product of these basis vectors with one another. So this is just a fact. You can check this. This just uses sort of just calculus. If you take e to the I n x and you take the inner product with e to the I m x, you can just check that this is 0 if n and m are not equal. And we just saw that this was 2 pi if n equals m, right? Each of these vectors has length square root of 2 pi. So if you take the inner product with itself, you get 2 pi. In other words, these basis vectors are orthogonal. Okay, and so not only do these functions have nice properties and do they form a basis, they're even an orthogonal basis, which is essentially the nicest kind of basis when you're in an inner product space. Actually, that's a lie, right? We know of things that are even better than orthogonal bases, and that would be an orthonormal basis. So we can normalize. So for each n, let's let phi sub n be 1 over root 2 pi e to the I n x. Now, I've just normalized every vector by dividing through by its norm. So this set is an orthonormal basis of V. So we've identified a very nice basis of this space of continuous functions. Okay, and that means that we can write every function, every continuous function, every function in V as a linear combination of these guys. So for every f in V, we can write f as, it's a linear combination, but it's sort of it's doubly infinite, of fn times phi n. Actually, I think the notes use fn hat. Actually, sorry, the notes do this. Let me try to stick with the notes. So this is n and z. Fn times root 2 pi phi n. Okay, and this is called the Fourier series. Either one, really, of f. Right, so what you've done is you've written every function in terms of a sum of a bunch of very, very nice functions. And the functions, these phi n's, are essentially trig functions, right? They're cosine plus I sine of something. Now, of course, this is, in some ways, you've made your life worse because now you're dealing with an infinite set of functions as opposed to just the function that you started with. But again, these are really nice functions, and if you just take the first few terms, you'll get a nice approximation of your function. That's really the magic of choosing this particular orthonormal basis. Now, because we have an orthonormal basis, it's actually quite easy to compute these coefficients, it turns out. This is sort of standard if you study just the first bit of inner product spaces in any textbook on inner product spaces. But since this basis is orthonormal, you can actually prove this yourself. The coefficients root 2 pi times f hat n are easy to compute. Namely, this coefficient is just the inner product of f with phi sub n. You can actually compute this just using the fact that phi sub n is orthonormal. Basically, all the terms cancel except for the phi sub n one, where you'll get a coefficient of 1, and so it'll pick out that coefficient. Okay, so this is, of course, just just the integral from 0 to pi, 0 to 2 pi, of f of x, right? And then e to the negative I nx, I need to take the conjugate dx, which means that fn hat is just, I want to interpret with phi n, so I need another 1 over root 2 pi here. E to the negative I nx dx, which means this thing is I just divide it over by another root 2 pi and plot the scalar. Right, and this is just a definite integral. You can numerically approximate this, for example. So this is easy to compute. This is just definite integral, which is easy to compute. Now, the picture that you should have, okay, is that V is some humongous space. And of course, by humongous, the picture I draw is three-dimensional. And these phi n's are chosen really nicely to form an orthonormal basis. And generally, you take all the ones from negative n to n, say. So it's like you build it up slowly, right? So like, okay, so phi 1 is, or phi 0 is some vector. Phi 1 and phi negative 1, I mean, these are all orthogonal to one another, right? But the point is that if you take the first n of them, say, so maybe this is the span of phi negative n, phi 0, phi n. It's 2n plus 1 dimensional, so it's a small dimensional subspace of V. And taking those terms in the Fourier series is like projecting your function onto this nice small subspace, right? So if you have f lives out here, but if you project it to this vector, this is the Fourier approximation. Okay, now of course, um, in general, a function could be very, very, very far away from this subspace inside of V. But the point is that when you're dealing with a signal that you're actually recording from something, you don't just get random noise, you get some sort of actual signal, right? And the thing to notice here is that the different phi n's, as you increase n, the period goes up. Or, sorry, the period gets smaller. The frequency goes up, right? The frequency with which we wrap around the unit circle goes up. So each of the phi n's, as the n gets big, are sort of more and more frenetic, right? And so, like, if you were approximating some function from 0 to 2 pi, right, so some function that you actually measured, functions that you actually measure end up looking like, I don't know, like this, right? Or like this. And so the first few terms of the Fourier series are giving you the ones with the longest period, right? So, okay, this is just a sketch, like, but like maybe the first one looks something like this, right? It's a very even thing. Again, I'm these are all complex functions, so I can't really be drawing the picture, but and then maybe the second function has like twice the period, right? So maybe it goes like this. I need to draw some more symmetric looking functions probably. And as you take more and more and more terms of the Fourier series, of course, we should be adding these together, but regardless, you're getting like more and more little tiny oscillations. But it's sort of clear that the first few terms should be mostly shaping out what this green wave actually looks like. And so because data that you record, waves that you study, aren't just random continuous functions, they are sort of very nice continuous functions, this red plane, giving you the Fourier approximation, is quite close to most of the functions that you actually get. And this Fourier basis is an orthonormal basis of this space, this red plane. And that's really why Fourier analysis works so well. It's because we've identified a really nice basis of the space of all continuous functions, so that the functions that we look at in practice are all relatively close to the subspace spanned by the first few of these vectors. Okay, so of course I haven't I haven't told you how to compute these things. I mean, I told you the equations, I guess, but I didn't compute any examples or anything. But hopefully in the future, when you see Fourier analysis in your other classes or at work or whatever, you'll understand why Fourier analysis works from a linear algebra perspective. Okay, I should also talk about the discrete Fourier transform, which is maybe even more useful in practice. Because notice that all of this stuff that we just did requires me to know my function f, right? If I want to compute these Fourier series, I need to take the inner product of f with these phi n's. So I definitely know the phi n's, but maybe you don't have an expression for the function f. In general, you're not, like, when you collect data, you don't collect an algebraic expression for the function. You collect a bunch of data points along the function at discrete time steps. So what the discrete Fourier transform does is it allows you to do this Fourier business without knowing the function, and instead just sampling points evenly along the function. It's like, instead of knowing the entire green curve here, it's like I knew this point and 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 this point, right? I need to sample them evenly. And that's actually not mentioned in the notes, but it's actually very important. But I want to be able to do some of this approximation stuff, but I only have some of the points, some sampled points on this curve. How do I do it? You do this with a discrete Fourier transform. So again, I'm just going to talk in broad strokes here. So suppose that we have a set of measurements at some evenly spaced points x0, x1, and I'm going to go up through x capital N. This is slightly different from those. I think we should, because I want to use little n for something else. So these are, of course, these are just in R. I guess for me, these are in 0 to 2 pi. And so if what we've measured is we've measured f0, f1, fn. These are values in C. So again, you just imagine these green points are xi comma fi, right? So where presumably f0 is equal to f of x naught, right? It's like we've observed the function at n, capital N, I guess capital N minus 1. These things only matter a little bit. Okay, now f, there's some function f underlying these data points. We just don't know the function, but we should still be able to come up with an approximation to what the function f would be in terms of our basis vectors. Right, so we can still get a Fourier series to fit these data points. In other words, what we want is we still want a function that's a sum of the phi n's, right? Or the e to the I n x's that look like this. Let's say phi n. No, I think I actually want e to the I n x here. Again, it doesn't matter. That's just a matter of scaling. And the formula is fn hat is going to be the sum from j equals 0 to capital N minus 1 of this fj. So this is a sum over all of the data points that I've collected. Right, so I do fj times e to the negative I 2 pi over n j n. Okay, so this is just the formula that tells you how to get the Fourier coefficients. So these things are called Fourier coefficients. Maybe I didn't say that earlier. And notice that this is basically just a discrete form of, it's very close to a discrete form of this integral. Or maybe I should say, I guess, of this integral. It's just that we now can't take the integral because we don't know the function f. What we know is we know capital N points on f. And so instead of taking the integral, we have to add up a bunch of things. And this is just the correct thing to approximate this integral with n data points along the interval. Okay. But the point is that this thing actually is very nice, right? So now in order to get these Fourier coefficients, we don't actually need to do an integral, which what we had before when we took the function. Now we just need to do a finite sum. And so computing each Fourier coefficient is now something that's very easy to do numerically or computationally. Okay, so let me introduce some notation to talk about how we do this. So we'll let omega sub capital N be e to the negative 2 pi I over n, aka cosine of 2 pi over n minus I sine pi to 2 pi over n. Okay, and notice that if you take omega n to the nth power, you get e to the negative 2 pi I, which is just 1. Okay, so what is omega n? Omega n is one of the primitive capital nth roots of 1. Right, so this is a picture of C. Omega n is just a complex number. Here's the unit circle. And what omega n is it's this vector. This is omega n, where this angle is 1 over nth way around. Right? It's 2 pi I over n, which means it's 1 over the nth way around. So omega n squared, remember you just add the angles. Here's omega n squared. Here's omega n cubed. Dot, dot, dot. Here's omega n to the n minus 1. And then omega n to the n is just 1. So what omega n is just the first clockwise point if you distributed n points uniformly around the unit circle in the complex plane. So this is like, you would call this a primitive, one of the primitive capital nth roots of 1, or capital nth roots of unity, is sometimes people say. If you see that, that's what that means. Okay, so now with this omega n, notice that this term here is just omega n to the j. This is omega n to the jth power. So what you're doing is you are raising this omega n to the jth power to the nth power, where n varies, I mean, depending on which the Fourier coefficients you want. When you want the first Fourier coefficient, you just take omega n to the jth power, you sum that up from j equals 0 to n minus 1. When you want the second one, you square all those things, etc. Okay, so then we can just write down, you just check this, right? So we have n minus 1 of these Fourier coefficients. Each of them is a sum of fj times some power of omega n. In other words, you can think of this as a dot product of two vectors, right? You can think of this as the dot product of some omega n vector, so omega n squared, right, omega n to the n minus 1. Really, I should put to the nth powers here, dotted with this vector. Right, that's another way to think about what these things actually are. So this, if I combine those all together, I'll just take the following matrix. So here, omega n squared, omega n to the n minus 1, 1, omega n squared, omega n to the 4th, omega n to the 2n minus 1, omega n cubed, omega n to the 6th. This goes all the way down to omega n to the n minus 1, omega n to the n minus 1 times n minus 1, times our collected n data points. In other words, the Fourier coefficients, you can compute them all at once here, at least the first. I mean, if you want to compute the first n of them, 0 to n minus 1. This matrix will just tell you what those are. Okay, so this matrix, called Fn, is called the discrete Fourier transform. So if you have a bunch of data points, then you can easily get the coefficients on this Fourier basis to give you a function which approximates something that would fit those data points. That's the idea. And then even you can speed up this computation even faster if you want. So computing this vector, which is multiplying out these matrices, requires n squared big O of n squared computations in order to do it this way. But there's sort of a tricky method that computes it in n log n. So if you use the fast Fourier transform, the FFT, this is O of n log n, which is much better computationally as n gets large. In other words, as you get more data points, right? And right, if you're sampling some sort of wave, right, and the wave looks like this, whatever, this means that you might have like one data point every millisecond or every nanosecond or something, right? And so n does actually get large if you're trying to approximate this wave using some Fourier approximation. And I don't want to go through the details of it. That's in the notes. What I would like you to go away with in this lecture is how the heck is this a linear algebra problem? And essentially all of the linear algebra is here. That these functions form an orthonormal basis of all of the continuous functions from 0 to pi to c. All right. Hopefully you enjoyed this class. Hopefully you at the end of this class at least appreciate that linear algebra has an unbelievable number of applications even in the real world, which we just scratched the surface of. And as you go off to do whatever you want to do, whether you go off to do more math, more computer science, or if you go work as a software engineer or whatever, in lots of cases, in lots of these paths, knowing linear algebra very deeply is going to be an asset to you. And so hopefully this course strengthened your knowledge of linear algebra. Even if you don't remember everything from the course, nobody remembers everything from a course that they took. The next time you learn it, you'll learn it better. So if you need some of these things in the future, you'll be able to learn it, pick it up much faster because you've thought about it once. All right, it was a fun course. Thanks for bearing with me during these COVID quarters, this weird online stuff. But I guess I won't see you next time. Good luck and have a nice end of the quarter. All right.